Learning Objective 3 from Section 2.3 is to calculate p-values and determine statistical significance in hypothesis testing by randomization and simulation methods. Suppose you want to determine if yawning while asking people a question makes it more likely that they will yawn when answering your question, or if they are equally likely to yawn or not yawn. Also suppose the results of the experiment show that 17 out of 30 subjects yawned when you yawned while asking the question. You want to conduct a simulation-based test of significance to see if these results are significant. Which of the following describes the main assumption behind the simulation you conduct? When we conduct a simulation, we're basing it on the null hypothesis. We're creating a null distribution of what we would expect to see if the null hypothesis is true. Remember that the null hypothesis is a statement of equality, and it's not about the sample results, it's about the parameter. So the 17 out of 30 subjects that came from the actual study that we did will not come into play as part of this null distribution, as part of the simulation that we conduct. The simulation is going to be based on the statement of equality about the parameter, which we can find right here, if people are equally likely to yawn or not yawn. So we're going to create our null distribution based on that statement there. So the 17 out of 30 won't come into play. We can eliminate A and B. And remember that the null hypothesis is a statement of equality. So let's look at C and D. Each person has a 50% chance of yawning when being asked a question, or each person has more than a 50% chance of yawning when being asked a question. Again, we base our simulation null distribution on the statement of equality in the null hypothesis. So each person has a equal to 50% chance of yawning when being asked a question. Let's look at another example. A popular uprising that started on January 25th, 2011 in Egypt led to the 2011 Egyptian Revolution. Polls show that about 69% of American adults followed the news about the political crisis and demonstrations in Egypt closely during the first couple of weeks following the start of the uprising. Among a random sample of 30 high school students, it was found that only 17 of them followed the news about Egypt closely during this time. To test whether the proportion of high school students who followed the news about Egypt is different than the proportion of American adults who did, the following null distribution is based on 100 simulations. Estimate the p-value and determine the conclusion of the hypothesis test. So I have a null distribution here based on the assumption that p equals 0.69, which is our null hypothesis here. That's the claimed population value. And now we're going to compute our p-value based on the sample results. Our p-hat is 17 out of 30, and that equals 0.567. So we want to find the results of that value or more extreme. Now, more extreme for this example is in either direction because we're talking about different than. So if we were talking about less than, we would be interested in only the results that were our results or smaller. If we were talking about greater than, we would be only interested in the simulations that were our results or larger. But because we're different than in our alternative hypothesis, we want to include both tails in our p-value. So let's find where 0.567 would be. 0.567 takes into account these first three stacks of dots, because that's where 0.567 would fall. Let me make this a little bit bigger so that we can count the dots that we see. There's one dot, and then two more here, so we're up to 3, 4, 5, 6, 7, 8, 9, 10. So we have in those three stacks that are our sample results, or further in the left tail, we have 10 out of 100. But because this is a two-sided test, because we're interested in more extreme in either direction, we're going to multiply 10 out of 100 is 0.1 times 2 so that we can include both tails of the distribution. We get a p-value of 0.2. Since 0.2 is greater than our significance level of 0.05, we conclude that our results are not unusual, and so therefore we would not reject the null hypothesis. Let me write in that conclusion. so that you can see it. The sample proportion is 17 out of 30, which is 56.7%. The first three stacks of dots represent sample proportions that are this value or lower, which total 1 plus 2 plus 7 equals 10 out of 100, or 0.1. Since this is a two-sided test, the p-value is about 2 times that left tail, which equals 0.2. Since the p-value is greater than 0.05, we fail to reject H0. The data do not provide strong evidence that the proportion of high school students who followed the news about Egypt is different than the proportion of American adults who did. Our results here are not statistically significant because our p-value is higher than our significance level. Let's look at another example. A common medical procedure that has been used for many years is effective in 31% of cases. A new method for performing the medical procedure is developed, and researchers would like to determine whether it is more effective than the old method. Notice here that we're now talking about more effective, so we're only interested in the right tail. In a random sample of 50 procedures using the new method, 26 were effective. Below is the output from a Rossmann-Chance applet showing the distribution of sample proportions in 10,000 simulations under the null hypothesis. Give the p-value and use it to determine whether the new method is more effective than the old method. So our p-hat in this case is 26 out of 50, which equals 0.52. And because we're only interested in the right tail, the Rossmann-Chance applet has marked for us the values that are greater than or equal to our sample result of 0.52. And it tells us what that proportion is, which is 0.0015. That is our p-value. So if you have the results of the simulation, then we can just find the p-value from the Rossmann-Chance applet. Here's the conclusion. The p-value is the proportion of simulated sample proportions that are greater than 26 out of 50, which equals 0.52, which is given by the applet to be 0.0015. Since the p-value is less than 0.05, our significance level, the data provides strong evidence that the new method is more effective than the old method.